Look, I get it. That's a lot of information to digest at one shot. Let me give an example, and I think it'll be a lot clearer. Let's say we have this causal input. Now you'll notice that this is the same one that we evaluated in the beginning right here with the power series input example. And let's say we're providing that input to the discrete time system whose impulse response is given here. And so there's two methods. Method one is the exact method using Z transforms. So to do that, we find the transform of our input, which we can do now. We've done so many of these things, we can do that just by inspection. We take a transform of our system. Now think about that for a second. What is the Z transform of this system just by inspection? And if it's not clear to you, try writing what your H of n is. Do you see how it's equal to an impulse at 2 plus 6 times an impulse at n minus 1? So can you see what the transfer function is? The Z transform of that in the frequency domain? You can read it right out. 2 plus 6 with a delay. Big picture again, look at what we just did. If you've got an input that lasts forever, like this input, look it up on your tables. If you've got an input that's finite, you can read it right out just by the definition of what the H of Z is, right? Because you know that the H of Z is defined, that's that third line, to be the sum over all n of whatever your input is times Z to the minus n. So you can read it right out. Okay, that means that our output, since we're convolving the two in the time domain, we multiply the two in the frequency domain, and it's our input times our transfer function. So it's going to be 2 plus 6 Z to the negative 1 all over 1 minus 1 half Z to the negative 1. And there's a couple of ways that we can do this. Our standard way is to say, hey, is this proper? Not proper. So we're going to have to divide it. And when we divide it, we're going to have to use long division, and we have to reverse the order of our coefficients. So we reverse the order of our numerator and our denominator coefficients, and we say what times negative a half is equal to 6. Pretty clearly, that's negative 12. It'll give us minus 12. And I'm bad at subtracting things. I'm much better at adding things. So I'm going to multiply the bottom by negative 1, and then I'm going to add them. So 6 minus 6 is 0. 2 plus 12 is 14. So this is going to be plus 14 over, and then I'm going to reverse my coefficients again to put in the sort of the standard form. So now I can write this as a proper fraction this way. And so now I can directly read this thing out. It's equal to minus 12 times an impulse plus 14 times 1/2 n u of n. But there's our second method too that we can use by approximating the result as the steady state response. To do that, firstly, we're going to have to make the input look like e to the j omega naught n. We did that on page 1. Just to repeat ourselves, all that we're saying is that our input, which we know is 1/2 to the n, that's our steady state portion of it. We're just ignoring our u of n. We have to make that look like e to the j omega naught n. So we can take the ln of both sides. And when we do that, we get n ln of 1/2. And the ln of e raised to the something, the ln undoes the e. And so we get just this. N appears on both sides. So we can divide through by n. And now we can divide through by j to say our omega naught here is equal to the ln of 1/2 over j, which I know is a pretty weird looking frequency, but just go with it for now. Our second step is to find the steady state response. And the steady state response is equal to the input times whatever our transfer function is doing at that particular frequency. So our input is 1/2 to the n. And what our transfer function is doing at that frequency is we take a look at our h of z. Our h of z is here. And we're going to convert our z to the negative 1 to a dtft. So instead of z to the negative 1, it's going to be minus j omega naught. But we've just figured out what our omega naught is already. So we'll substitute that in. And now we've got e raised to the minus j, and it's ln of 1/2 all over j. And that looks pretty messy. except we can see that our j's cancel. And now we're left with e raised to the minus ln of 1/2. We don't like this leading minus. If it didn't have this leading minus, we could recognize that e to the ln, the e's and the ln just undo each other and we get 1/2. But this negative sign, we can't do that with. So I'm going to take that negative sign right out of here. And I'm going to say that's equal to e to the ln of 1/2 to the -1. And what I did there algebraically is in this side note, where I just made c equal to -1. And so now I can continue the simplification. E undoes the ln, and we're just left to the 1/2 raised to the -1. And of course, 1/2 raised to the -1 is 2. 2 times 6 is 12. And now we can simplify that all down to times 14. Now from our previous work on this slide, you'll notice that our overall output is equal to the steady state response plus the transient response. Now this is an FIR filter, and for this FIR filter, our M is equal to 1. It goes up to, it's non-zero only up to N equals 1, so therefore our M is equal to 1. If we were to write this as a difference equation, I'll write it up on top of here, it means our current output is equal to 2 times our current input plus 6 times our past input. And so since this is -1, our capital M is +1. And that means that this is equal to our exact solution for n greater than or equal to m, which in this case means n greater than or equal to 1. And that's exactly what we find. This is exactly equal to our exact output as long as n is greater than 1. And for as long as n is greater than or equal to 1, and for n equals 0, it's off by this impulse. Okay. Just a quick thought question. What would happen if the input was equal to 2 times 1/2 to the n, u of n? Think about that for a moment. I hope it's clear after a moment's thought that all that differs is that our z transform of the input varies. This becomes, instead of a 1, it becomes a 2. And that means that our y of z would now have twice the numerator, and our y of n would be twice times this. In the steady state approximation, nothing here changes, with the exception that we would just add a 2 in front of here. The frequency stays the exact same. This stays the exact same. X of n is the exact same over here. But now you just put a 2 out in front of here, and then the 2 comes right out here. And that would be the same as what we get here, just times 2. And still, our transient solution equals the exact solution for any n greater than 0. For n, in other words, for n greater than or equal to 1.